The next session, Radical Technologies. Just to tell you a little bit about the format, we will have one keynote speech, and then our keynote speaker will join me and two others on the stage for a little bit of chat. Here again, get your Mentimeter ready. If you want to put questions to the speaker, there will be a couple of roving mics here in the room. Everyone online and at home can send in their questions. I'll have an iPad, we'll go through the questions. It looks like there's been plenty of engagement, so we'll have plenty of questions to go through, which is good, perhaps difficult to choose which are the good ones. For the keynote speech, to kick things off in this session, it will be Karl Deisseroth, D.H. Chen Professor of Bioengineering and of Psychiatry and Behavioral Sciences at Stanford, and investigator of the Howard Hughes Medical Institute. Professor Deisseroth, all yours.
Well, thank you all for being here. I'm delighted to take this opportunity provided by the Millennium Prize folks, and I'm very grateful to the people of Espoo in Finland for their hospitality and their forward-thinking spirit exemplified here. And I'm delighted to talk to you about some radical technologies and things that bridge fields perhaps in an uncomfortable way, but a way that brings immense opportunity. I'm a psychiatrist at Stanford. I'm also a bioengineer. Those are two fields that don't get to interact with each other very much. And if they do, you might imagine there could be some questions that arise. And that's certainly the case here. Now, I encounter patients who experience altered realities, people who suffer from disorders that are hard to articulate, but are very real and very biological. And part of my goal has been to establish the physical, biological realities of disorders that can seem very intangible and hard to put your finger on. I've gotten contacted by patients who express profound dissociation. After a traumatic experience, they're unable to feel emotion about events. They're fully aware of all the events. It's not as if they're anesthetized. They're fully cognizant of all the information that the environment has for them, but they don't feel emotion about it anymore, and a very debilitating and upsetting outcome for them. And how do we approach this? How do we describe physically what is going on? And to do this, we've been building technologies that allow us to approach this question. Now, the brain is a beautiful and complicated structure. It's got an immense richness of cells and cell types. The different colored spots here behind me, this is a part of the mammalian brain called the hippocampus, and there are numerous different types of cells that are represented there. They're tiny, they're fast, they're fragile. It's very hard to understand what is actually making things happen, what's actually causal in giving rise to the magic and the mystery and the power of the human brain. Now, people have thought about this. Francis Crick of DNA structure fame became sort of a thoughtful neuroscientist in his later years, and he said in 1999, we need a way to turn the firing of neurons, brain cells, of one or more types of those cells on or off in an alert animal in a rapid manner. And he said, what if we could do this with light? Light could penetrate. It would be fast. This seems far-fetched. Crick was brilliant. He posed the problem very well, but he had no idea how to do it. Well, we can do this now. And we do this with biological molecules that have origins billions of years ago in the ancient archaeal oceans. The world 2.5 to 3 billion years ago was largely an ocean, and it was teeming with microbes. And energy was harvested from light using a protein, a biological molecule sitting in the surface membrane of those microbes that received a photon, a light particle, and moved one charged particle, one ion, across the membrane of the cell. And an ion moving, a charged particle moving, is a current, an electric current. And so what this is a microbial, light-activated current generator. And this, by the way, current generation is how neurons work. It's very much, of course, an electrical system. And so the solution turned out to be taking the gene, encoding a protein like this from microbes and putting it into mammalian neurons. And just over 20 years ago, I did the very first experiment along these lines. I took a gene from microbes and I put it into mammalian neurons, and I found that I could control them with light. And because it's a gene, you can use genetic tricks to get it into one cell type or another cell type, but not both at once. And that gives us the leverage that Crick had asked for. And this is something that you can't do with electrodes or magnets because all neurons are electrical. So you can't pick out one type or another with electricity or magnetism. But if you can put one of these proteins into the membrane of a cell, and as it turns out, there's a wonderful diversity of these kinds of proteins. Some move positive ions, some move negative ions. They respond to different colors of light. And so you can build up a beautiful armamentarium of tools to turn cells on or off with different colors of light. And we call this optogenetics. How do you get the light in? Well, there's a few ways we can do it. We can use fiber optics. We can send light straight into the brain of a rat, for example, as shown here. That works really well. And the advantage of this is it takes a big step beyond where neuroscience had been. We had ways of probing neurons before, but they were physical. They involved electrodes or glass micropipettes. Hodgkin and Huxley in the 30s up to the 50s did experiments by putting glass micropipettes into neurons and neural structures, and this was beautiful work. They were able to identify this electrical event, which is called an action potential. It only lasts about a millisecond or so. This is the currency of information flow in the brain, but their methods were very invasive. You couldn't put 100 or 1,000 of those glass micropipettes into the brain of an alert moving animal, right? But using light, we can actually even do things like project holograms of thousands of spots of light into the brain of an alert animal that's carrying out complex tasks, and we can turn 1,000 or more individual kinds of cells or individual cells on or off as the animal carries out complex cognitions and computations and decisions. And so this is the leverage that Crick had asked for and that we can now achieve. I'll even show you a movie of this sort of technology in operation. What we see here, I'm going to play this movie in a minute, but these are individual neurons, each one about 25 millionths of a meter wide, in the brain of a mouse. And all these ones labeled T, T3, T4, these are neurons that I'm going to be stimulating with a spot of light. And you'll see the fluorescence change as the neurons respond. We have a fluorescent indicator of neural firing to see how well we're doing. And then there are some non-targeted cells that I'm not driving in synchrony with the others. So here's the movie playing, and you're seeing here the trace of all the targeted cells, and they're all being stimulated together. And you can see them flashing together when I drive them, but the non-targeted cells are not. And this is by guiding spots of light exactly to these cells, and this is done in an awake animal where we're carrying out a decision-making task where the animal has to choose what action to take. So this has allowed us to disentangle what actually matters in the brain, what's causing perception, sensation, cognition, and action. Let's look at the animal behavior. One of these molecules, it's called a channel rhodopsin, CHR. We put one of these into the mouse brain, and as some of you, or probably all of you know, the right part of the brain controls movement toward the left side of the world and attention to the left side of the world. So you might ask, what if we stimulate the right part of the brain that's involved in motor action planning? Would we see some leftward directed actions and planning? So here's an experiment with a mouse. We've got a fiber optic in the right side of its brain, and we're starting to control the right part of its action planning network. You'll see a little blue dot appear on the animal's head when the fiber optic is active. The animal immediately wants to turn left, and is very vigorously turning left. As soon as we turn off the light, the blue dot turns off. The animal stops, looks up at us, no longer wants to turn left. Instantaneous control using light. We can get into more complex behaviors. What about an action that we take all the time, choosing whether to eat or not, to drink or not? As we found, there are particular neurons that control all our basic survival drives. We can instantaneously turn up or down aggression, motivation, parenting behavior. This is the level to which you can reorder the priorities of an animal instantaneously is quite remarkable. I'll show you in this movie, an animal that's fully sated is not thirsty at all. What I do is here I turn on the thirst neurons deep in the brain, and you'll see this animal exploring, not particularly interested in food or water. But when the light turns on right there, instantaneously very thirsty, and we can make a thirsty animal not drink just as well as we can make a sated animal thirsty. So this starts to be almost unsettling, I would say. And here, in thinking about this, of course, we can understand aspects of our construction and our design more deeply, but it starts to raise some questions, I think. And I like to show this image because it clarifies the opportunity that comes in these moments of seeming peril. This is an electron micrograph of a Drosophila, a fruit fly, showing a normal head of a fly. And this horrific thing is a mutant that has legs growing out where its antenna should be. And this is like a nightmare scenario, right? But this is a representation of some of the most powerful insights that came from developmental biology. Christian Nusslein-Volhard and Ed Lewis and colleagues received the Nobel Prize for their work in creating this sort of mutant because the precision of mutations that altered pattern formation, the logic of construction of an animal body, through disturbing images like this, allowed us to understand how our bodies are constructed, the logic that underlies our design. And it's a similar principle with optogenetics. What makes it unsettling is also what gives us the deepest understanding. Now, we're working on bringing this sort of technology to the study of human beings and to psychiatry. And we've been working on this in a number of ways at Stanford. We have recording that we can carry out both surface and deep in human brains. While human beings are undergoing tasks very similar to what the animals are carrying out, and we can look for findings that bridge the two species. As I'll show you, it's even been possible to do optogenetics in human beings, and I'll show you a movie of that later. But coming back to psychiatry, if you're interested in the applications of optogenetics to psychiatry, I've written about depression, I've written about mania, autism, borderline personality, schizophrenia, eating disorders. All these fields of psychiatry have been illuminated by applications of optogenetics. And I'll talk about one in particular, which is dissociation, which I mentioned at the very beginning. This is a painting by the American pop artist Andy Warhol, and you can see there are at least three different versions of his face in this self-portrait that are shifted from each other. People who are dissociating often are not only experiencing a separation of their emotions from their sensation, as I mentioned earlier, sometimes they even feel separated from their body in a very unsettling but precisely defined way, a certain distance, 3 feet, 6 feet. And this dissociation can take a number of different forms, but it all shares this principle of a separation of two aspects of brain function that are normally tightly integrated, unitary, but now separate. And this dissociation is one of the interesting things about it, even though it sounds a little bit unclear that it could even be real. It's common, not just in psychiatry. It shows up certainly in post-traumatic stress disorder, shows up in dissociative disorders. Drugs can cause it, like ketamine or PCP. traumatic experiences, up to 70% of human beings with no psychiatric history can dissociate after a traumatic experience. And as we start to see that it maybe has some adaptive value in allowing human beings to navigate through extremely traumatic experiences, shows up in epilepsy. And what gives me as a scientist, as a student of biology, confidence is that there's, across all these different etiologies, origins of dissociation, you have very similar descriptions. People have this common experience of being aware of information, but feeling less agency, less emotion, separated from it. A patient with a dissociative disorder, they say, I feel like I'm in the passenger seat of the car. Someone with a ketamine-induced dissociation says it feels like I'm watching a movie about my life instead of experiencing my life. And what we've been able to do with optogenetics is we've been able to create this sort of operation of the brain in the laboratory. We can understand how different parts of the brain can become out of sync with each other and unable to together form a joint representation of the same thing at the same time. And so this very intangible, fuzzy concept that maybe some people didn't even believe was real, we can now point to and say, this is exactly how it can work. That these particular cells and these particular cells are firing in a particular way that is no longer allowing them to form a joint representation anymore. And to be able to have this kind of physical reality brought to the field of psychiatry has been a great source of hope, I think, for the community, and will, in the long run, potentially reduce the stigma, reduce the isolation, the frustration, the anger, the blame that compounds the illnesses of psychiatry in such a profound way. I'll give you a couple other examples going beyond dissociation. Anxiety, the most common class of psychiatric disorder. Turns out that you can't understand it just by thinking about the brain, you've got to think about the heart too. The psychologist William James actually thought this was such a profound principle. He said if you didn't consider the bodily changes, there would not even be an emotion at all. He considered the physical changes, the pounding of the heart, to be intrinsic and required to define an emotional state. It was an interesting idea, but very hard to test because you couldn't causally, precisely just control the heart rate without affecting other things as well, like all the other cells in and around the heart. But with optogenetics, we were allowed to do that. We put in one of these microbial light-activated proteins into the wall of a mouse heart, and we fitted it with a nice LED vest. This was non-invasive, didn't even need a fiber optic. We had a very light-sensitive molecule here. And we found we could pace the heart at different rates. We could pace it any number of beats per minute we wanted in a freely moving mouse. And we could ask, does it matter to the mouse? And if so, how? To its affective or emotional state. And one thing we found is if the animal was in a neutral setting, it didn't matter. And we do this test called a place preference. We let the mouse move freely from one chamber to another, and we can set things up in a closed loop way so we only pace the heart faster when it's in one chamber. So whenever it happens to wander into here, we pace its heart really fast. When it wanders out, we go back to the normal rate. Turns out in these neutral contexts, one side is the same as the other, the animal didn't care. There was no change in its preference for one chamber or the other, even though its heart was pounding much more quickly in one chamber. But it mattered as soon as there was a meaningful context. And if you're a mouse, one thing you want to do is avoid being out in the open. And in this simple maze called a plus maze, there's an open arm that's exposed and a closed arm that's much more protected, has a roof over it. Mice love the roof, but they have to go out to explore sometimes into the open. And if we paced the heart much more quickly with a channel rhodopsin, the animal almost never came out into the open arms. And so the pounding of the heart, compounded with the perception of a potentially risky environment, together created what we would call the emotional or affective state. And this was a consistent finding across multiple mice, other anxiety measures. You can take a thirsty mouse and give it a small risk, a 10% risk of having a little buzz if it takes a drink of water, an aversive, annoying buzz like you would get with a joy buzzer. And normally they don't care that if they're thirsty enough, that 10% risk doesn't affect their speed to take a drink of water. But if you're pacing the heart faster, they take longer to take a drink of water if they know there's a 10% risk of getting that little buzz. And so multiple measures, apprehension in the absence of immediate threat is heightened by the pounding of the heart. And this is a causal, precise question that optogenetics allowed us to answer. Now, what about human beings? This is an example, work led by my colleagues Botan Ruska and Jose Sahel, introducing into a patient with retinitis pigmentosa, a fully blind patient, introducing one of these opsins, these molecules from microbes, into the eye of a blind person who cannot see, and asking, can we confer vision onto this person who was absolutely unable to see an object in front of them before? So this man is looking at a table. There's a notebook in front of him. He's looking for it. The light's not turned on yet. He's aware of the table. But on the table, he can't see anything. Now the light's turned on, and they ask him again, can you see it? And by the way, you can see what is coming through his goggles here. This is what he's seeing, at least what's coming through the goggles in front of his eye that allow us to see where his attention is being directed. You can see he's homed in on the notebook, and he can see it. Okay. So this was a transformative moment. This showed we could take, it's on the right, we could take one of these proteins from these ancient organisms, these ancient molecules, and confer vision onto somebody who couldn't see. Now, there are a lot of things we can do that are what you might call direct translation, putting the opsin directly into the nervous system or the body of a patient, but there are many other applications too. We could guide and develop medications this way just by knowing which cells are causal, which cells actually matter for symptoms or the resolution of the symptoms. And that you might call indirect optogenetics, which maybe is an even greater opportunity because of the ease, of course, of delivering medications compared to opsins, molecules from ancient organisms. But it exemplifies the exploration of nature and taking unlikely leaps, bringing a gene that was present billions of years ago and exists today only in single-celled microbes, and putting it into animals and into human beings gives us insight into our construction, unsettles us, but also provides real and tangible hope for the future. So I'll pause there. Thank you very much for your attention, and happy to take questions.
If I had a spare hand, I would be clapping really hard. All of the eyes backstage about this big. I am looking for, okay. We don't have any questions on the Mentimeter yet. I presume it's because everybody's waiting to do that in the room. We'll have some mics going around. Does anyone at the outset here have a question they want to ask? I will absolutely fill this time. Gentleman here.
Thank you very much for your excellent presentation. I'm not from the field myself, so is it technologically possible to control humans in the same way that you controlled mice in the video you showed? Thank you.
How many people had that question?
A very important question and a very good one. As you can see, the technology works in humans. Of course, that was the retina, not these deeper structures, but we know how to get the light deep. We can do it with fiber optics. There are ample clinical pathways for implanting long, thin elements into the brains. We do this with deep brain stimulation in human beings all the time, which are actually even larger than the fiber optics we would use. Similarly, there's no barrier to doing gene transfer into the brains of people. This is done routinely. There are hundreds of approved clinical trials using these very safe, modern gene delivery vectors called adeno-associated viruses into human brains. So there's no fundamental barrier. And then the final question is, are things similar enough from mouse and rat to human that you can be guided in a principled way by the laboratory work? And that is also likely the case because mammals, of course, we have much larger brains. They're scaled up in many ways evolutionarily, but the same basic logic, the same regions, the same classification, the reward structures, the fear structures, the motivational structures, the dopamine neurons, the serotonin neurons, all those things are shared and organized similarly in rodents and human beings. So there's no fundamental barrier, and it's more a question of what is the judicious approach to take, the careful, the ethical, the thoughtful approach, given the opportunity that we have.
Any other questions in the room? Here we go. Already at the mic.
Hi, Karl. Thanks for a great talk.
Thanks, Sarah.
So there is not only the patterning that you showed with the antennapedia or something like that, but there is also experiences and there's also learning that drives the brain. So it's not only the cell types, but it's also how we have learned to use certain individual cells there. So how do you go about sort of addressing this thing? How do you select the ones that are involved in this particular learned action?
Yes, so of course learning, plasticity, this is a fundamental part of how the mammalian brain works. One thing, we can certainly cause plasticity, we can cause changes in the brain with optogenetics, so that's one partial answer to your question. We can be the force that creates that change, if we will. There are patterns of activity, high frequency bursts of activity that can cause stable increases in functionality of a part of a brain or a connection, and we can do that with optogenetics. We can cause lasting changes. But the question was perhaps more about how can we adapt the stimulation to come not just to a cell type, but to a cell that has done a particular thing recently, or that has changed in a particular way recently. And this is also possible. We have, because these genes for microbes are small, and there's just one of them, they're easy to target. You can use genetic tricks to not just guide them to cell types, but you can guide them to cells that have had a recent burst of activity, a recent burst of intense activity, for example. And you could pick out cells that way. That's been done in mice, as you no doubt know, and in principle, this could be done in human beings as well.
Right, we do have some questions at last coming in here. Alas, it's going to have to be a very quick one, we're already out of time. But this is good because it keeps us very much on theme. You said during your talk that this was part of what we saw was unsettling. It raises questions, you haven't directly addressed them yet. Someone asks, what is the dystopian path you can imagine being the result of applying your technology?
Well, the contrast is, certainly we can change aspects of ourselves right now. I can drink coffee and I can become more alert. I can, if I like, I can take medications that increase my energy or my focus or my motivation. So to some extent, you might say that's not fundamentally different from where we are now. However, there is a difference in the precision and the speed. So a lot of these other things that we have available now are self-limited in various ways. They have side effects, they're slow, they're not as precise. And so what is unsettling and perhaps dystopian about some visions of the future you could have is that you could have people in the very long run modifying their principles and priority structures in very fundamental ways that would raise real questions about what is important about the self, what is important about a human being that should not be changed. Is it the priority structure? Is it the principles that we have? Is it how we rank our primary survival drives relative to each other? And maybe those are things that shouldn't be altered, and you could envision a dystopian aspect of the future where these parameters were too easily changed. I don't think that's likely. This is not an easy-to-use technology. It's a discovery engine for science. It helps us understand the brain more deeply. It helps us understand ourselves. And so I take a utopian perspective on this.
Okay. First of all, thanks very much for that. And
Thank you.
And if I could ask you to take, I don't know, a couple of steps forward, stand there awkwardly while I call up the panel. We'll move on to the panel discussion. I believe a lot of the questions that have come in will actually be tackled by this, so sit tight. I would like to invite to the stage Sabrina Maniscalco, a professor of quantum information computing and logic at the University of Helsinki, and Thierry Klein, president of solutions research at Nokia Bell Labs. A moment to thank the event staff who are working very hard behind the scenes. Please, take a seat. Right. Just, again, the housekeeping. There are 2 sessions that will include a panel, and I sort of see them from 2 perspectives. One of them is the technology from the practitioner's point of view, sort of from the ground up, when the science becomes the technology, becomes the product. Later session is going to tackle more once the technology is out in the world, once it's in human hands. So try to keep a perspective from there. And I think we want to start nice and high level because we have just been presented something with some research that raises some questions. And I think in a general sense, people have some worries, sometimes very deep worries, very existential worries about technologies. I'm not sure they always align with the worries of the practitioners, of the scientists, of the people who are at the making end of this. So first question kind of for everybody. And I'll start with you, Karl, because it sort of follows on here. The worries that people have about technology, in a general sense and about your own work, do they line up with your own worries, do you think?
When I hear the worries people have, they align very much with things I've thought about. I think I haven't heard an unreasonable question or an unreasonable concern. And so at that level, I very much welcome, even from, or especially from lay people, what their worries are, what their concerns are, because they're usually right, I think. At least in principle. It starts the conversation. That's the key thing. We have to have the conversations going early before it's too late. And I think our discussions on the ethics of technology always have to start with human stories, have to start with what matters to people at the outset.
Sabrina, are we worrying about the right stuff?
Well, in my field, that is quantum computing, of course, in some cases, that's correct, but there are also worries which we find unjustified, or at least they should be considered under the right light. And one example for quantum computers is one of the applications is breaking cryptographic codes, and so our concern is that this is something that could be a threat for national security. And a lot of actions and regulations have been proposed precisely due to this, and the whole geopolitical situation has been dominant in deciding about this technology. And in truth, this is something which is really at this stage, a very, very, very early stage. So the algorithms that would allow to break cryptographic codes are algorithms that have never been really tested on devices that would be really at a scale that would constitute a threat. So we don't know actually if this will ever happen. So clearly it's an important thing to consider, but there are other applications that are much more near term and that are very often unforeseen that actually could be more I don't want to use the word dangerous because it's really not the question of being dangerous, but they could happen before and they could change our society. And this leads to the problem of regulating early or late, but maybe we will touch upon this later.
So yes, worrying about the right kind of stuff, sort of no, worrying about the right kind of stuff. Thierry?
I think I'll be more on the no, I'm worrying about different things. So I'll come from the AI perspective. I think there's a lot of fear that AI will take over and the world will be dominated by AI, bots, machines, robots. I'm not worried about that. I'm I'm coming a little bit more from the business perspective because there's so much investment going into AI. I'm coming, where's the actual return on all that investment? So are we applying it to the most important problems? There's so many different use cases and applications for AI today. If you think about Gen AI, but AI more generally, are we actually applying the technology we're developing to the problems that matter, that actually improve, whether it's productivity, efficiency, safety, sustainability, or are we doing it on, I don't want to say frivolous, but use cases that actually don't really matter to industry or society?
I would like to follow up on that, because when you talk about problems that matter, and forgive me if this is a very cynical question, but we've seen that some of the worst outcomes from technologies have been sort of optimizing on shareholder value. When you come from the business perspective, sometimes we become misaligned, right? What's best for the business isn't necessarily best for society. I won't name any examples, but I know you've got some in your heads. How to get those realigned? In your work, how do you keep those things on the same path?
Well, I think ultimately they are aligned, because you create shareholder value if you create products and solutions that people will use and that serve a purpose. So I do think that ultimately they need to be aligned. But you had the example earlier about the billionaires who are pursuing their childhood dreams. I think that's not the majority of industry or companies in the world right now.
Right. Do you guys have thoughts on that, on how to keep the sort of, if business pays the bills, how to keep the products aligned with what we actually want?
Of course, this is a general concern, and it really depends on the specific case or applications, but in our case, what we do has to do with the development of methodologies to simulate in silico medicines and drugs using quantum computers. And obviously, you can use this for good or for bad. I mean, it can create really a new society where we are able very quickly and efficiently to produce and distribute to everyone drugs, but it can also be used for, I don't know, bioweapons. So it's again the question of really the applications and the integrity that we have in making sure that what we do is done for the good of society. Technology is neutral in this case. So and obviously the applications in medicine and healthcare and medicine also would bring value to the business, certainly. So it is in itself not something that is in contrast with what shareholders would want.
Do you have thoughts on that?
Well, yeah, economic considerations are interesting when you come to consider healthcare and interventions in human beings. It, first of all, does provide a self-limiting principle, and so to Thierry's point, that has some value because it aligns what is done with what actually matters most to people, and the economic aspect actually can, in that from that perspective, can help correct decisions be made, I think, from the healthcare perspective. But then you also can have an awkwardness with access. And there's an awkward middle ground where a few people might have access to the technology, but not everybody. And then there are questions about is that fair? And if it's a powerful enough, life-changing enough, intervention, then you have some questions to deal with.
We'll come back, I think, to the access question. But
so that's a point that I would agree with a lot of the concerns about whether it's AI or technology in general. Is the power of technology concentrated in the hands of a very small number of people and companies, and how do we democratize access to the technology? And I think particularly what Karl presented, which is fascinating but quite scary, how do you make sure that if there are benefits to that technology and society would benefit from it, how do you make sure that everybody would have access to it versus just a very small number of people? So I think the worry of how do you make sure the technology serves everybody rather than a small number of individuals that can afford it or that hold the keys to the technology.
Sure, and we've certainly seen this with technologies before, and the degree to which the best stuff we have in our pockets here is not widespread if you look at the whole Earth. So we're all agreed, I think, that that's a problem. What's the solution? How at that sort of base level, practitioner level, do you try to ensure that everything gets into everyone's hands?
want me to go first?
Well, you did post the question.
Okay, so I come again from the AI perspective and data. I think one of the speakers this morning mentioned that we need to have lots of different language models, for example. I don't believe that we should just have one large language model or a small number of large language models that everybody has to use, because that's concentrating the power in those who have the capabilities to develop and run those models. I think we should be thinking of a way of making it easy for everybody to build their own models, because they have a particular domain that they're interested in. They're not necessarily interested in a single language model that can solve all the world's questions, but you have a particular domain that you're interested in that has very special questions, special language that you want to use, whether it's inside your company or inside your particular industry sectors. How do we make it such that everybody can develop their model? It may not have the power of the large language models, but maybe the right model for solving your question. So we very much believe in sort of decentralized, distributed systems where everybody has data. And data is being generated in a distributed way, but AI models are not created in a distributed way. So how do you allow you as an individual, as a company, to build your own data models and language models and apply them to your own problems? So how do you enable that? And there are actual technology advances that allow these decentralized distributed systems to operate.
Sabrina, I know this has particular resonance with you because quantum computing sort of necessarily relies on big, heavy, expensive stuff. How do you think about that question of access?
That's correct. Well, the way in which I try to contribute is really in participating both in the dialogue with policymakers and with institutions that have the power to influence really or the access really of quantum computers and how it is regulated. And then there are certain institutions or certain associations, JESDA is one of them, the Geneva Science and Diplomacy Accelerator. They are really, they were born with the goal of democratizing quantum. So to make sure that this is, since the very beginning, something that is in the agendas of politicians, it is the agenda of the European states. So, and in a way, I think the best way I have to contribute is to participate to the dialogue of these institutions and try to push it in the direction where these important questions are in the agenda, whether it is the World Economic Forum or European discussions or at national levels. So I think it's important because eventually they will decide and they will have the power to make it happen.
You're pointing then to the idea of institutions solving this problem, not letting businesses solve this problem, not imagining it will simply sort itself out, because we know that doesn't work. It's an institution level problem.
Yes, I think that, I don't know if this is the only solution. Of course, there is not just one entity that will be able to solve it, but that they can push really dialogue and try to find solutions and compromises, which involve obviously also industries. But it is probably not in the industries, let's say, best interest in some cases, So you need to have some super partes institutions that promote this and therefore create agreements in businesses and make it possible. And so my contribution is to, in a way, be there and participate to these discussions for this to happen.
Karl, you first brought up the notion of access. Do you want to add to that?
Just briefly, that certainly in healthcare and medicine, we see that equity lags, but it gets there in the end. And just as with many technologies, medical interventions most of them were initially inaccessible, too expensive. But then, if we trust to economies of scale, if we trust to scaling laws, after some time things become equitable again. It would be a shame to stifle growth because of that lag. I think we have to acknowledge that it's there, minimize it as much as we can, but not let it stifle innovation.
At the mention of stifling innovation, so you bring up institutions, you bring up stifling innovation. That is just as good a lead-in to regulation as I'm going to get. These sorts of discussions always have a giant carpet under which everything gets swept, which is let the regulators do it. But when we're talking about really emergent technologies, potentially transformative, Where do the regulators come in? We know from the technological world that we've got that regulators, regulations are not keeping up with the pace of change. If you send them in, like the troops to solve this problem too early, you stifle innovation. If you wait too late, now you have a problem, for example, with the technology that has become very centralized and you can't put that genie back in the bottle. What role do regulators have here as the sort of the alleged police of this? Everybody says, oh, well, the regulators will solve it. Not so sure. Who wants to start on that one?
Well, I'll just briefly say that in the U.S. we have, on the healthcare innovation front, we have regulatory agencies which mostly operate well. At their very highest level, though, they're political appointees, and so there are cases where politics can affect the operation of these agencies, and that's always a potential risk. But in general, I think from our experience, the healthcare regulatory spirit and practice is fairly positive.
Which is to say, it starts where? It starts when? Right at the ground level.
It starts when?
Yeah. Regulators, hey, look, this could really get out of hand. You guys should come in here and make some rules for us.
Yeah. There's an instinct, I think, too, if you come in too early, then you do get the stifling effect. But in the case of healthcare, there's a natural break point is when you start to put things into people, and there, I think that's when the regulation can and must be present. So I think it's on my end, it's a much clearer red line. I think it's much harder for the other two panelists.
Well, moving on. You were chomping at the bit. What do you think?
So I think that's probably the hardest question you could ask.
Should I have saved it for last?
That's fine. I think it's really the challenge of you want to drive innovation, you want to come up with the new technologies, because ultimately, from a technology perspective, you have this hope that technology will help improve things and solve some of our challenges. But what's the right time? I think it's the hardest question, but I think the question is not just when should regulators come in, it's also you have a particular domain that you want to apply the technology. And then how do you guard against derivative use of technology for other uses that you may not want? So it's not just when do you come in, but also what are the boundaries you try to put on it. And maybe the only thing or one thing I would add to address the challenge is we need to shorten the loop between technology, industry, universities, research, and regulators and governments. You said they come in too late, or they get afraid and then they regulate too quickly. I think we maybe we need to shorten that loop and give them early insights. I mean, AI did not start with ChatGPT. AI has been around for a long time. And now it seems like it moved to more the popular domain, and all of a sudden everybody's in panic about AI and how do we control it and how do we make sure nothing bad happens. I think we need to maybe shorten that time frame when regulators or governments pay attention to technology. And I think that's a role for everybody on technology, on research, to share the potential of the technologies, even when they're very, very early, saying, we don't know that this will work, but we're exploring in this direction. And if it works, this is the potential, these are the pitfalls. So that maybe that time frame is a little bit compressed.
Sabrina?
Yeah, I think that regulators should monitor and continuously dialogue with the scientific community and with the innovators until the point in which there is an understanding of applications that are proven as proof of concepts at a scale that is undeniably proving, applications that could be used for good or for bad. But for example, in quantum computing, what happens is that we have had this year, a remarkable year in which we reached scale of quantum computers that can be really challenging any classical device. So this is an important point. However, we need to have access to devices from all over the world in order to figure out which applications are useful to end users. And so if you regulate now, definitely you are inhibiting this process. So this is an example because we don't have yet, the alignment between, or the proof of an alignment between end users and technology, the level of technology. We have a lot of indications, and we have an inflection point, really, which has happened. But regulating now, it is a really serious problem. Yeah.
You mentioned along the way there things that can be used for good or bad.
Yes.
That whole dual-use notion.
Yes.
I think a lot of people agree with the idea that in one way or another, every technology is dual use. I mean, how do you think about that? Put the regulators aside. You're alone with your work, with your colleagues, at a conference, what have you. How do you deal with that notion? Karl, when you were speaking, I was thinking very much about, I think as many people in the room would be, about how could this be used for ill? You say, it'd be really hard, but everything looks hard on a long time horizon. How do you deal with that notion of this could be used for ill? And what I was thinking during your talk was, are you obliged as a part of your work to sort of like sort through that, the ethical considerations, the ways this could go wrong?
Yes, there's not a formal obligation apart from regulatory considerations when you start bringing things into people. There is a implied obligation to consider ethical perspectives, and we do that. There's a growing field that centers on neuroethics and neurophilosophy and the legalities of changing the nervous system. It's a thriving field and some very interesting writing, journals, and it's a growing community, a community that's going to be very important going forward. I think engaging with them is going to be very fruitful. And I think always coming back, starting and ending conversations with human experiences is very important. That's what grounds us in what really matters. It'll help us be sure that we're doing things that are aligned with human values. And this is something that in medicine, of course, we always are thinking about what are the ethical considerations with a particular kind of treatment. This is new, though, in some respects, and I think it requires a special integration with ethics and philosophy.
So your argument, at least in your case, is that at a community level, these things are being addressed, and you have some confidence that, at least for your work, the right questions are being posed, and the right paths toward a dystopia being blocked off.
That's right, and the right path, I think, is a middle ground. To be clear, there could be an instinct to say you should never do this, and there could be an instinct to say we should do everything we can. And in this case, although it may be a boring thing to say, I will say there is a middle ground that is the right one to take, and I think we have an emerging consensus that is the path.
Little column A, little column B.
That's right.
Let me put that to both of you. Would you say in your field that at a community level people are asking the right questions and addressing them? As regards dual use, for example.
Okay, yes, related to dual use. Yeah, of course, they are. The question is not per se, whether the technology, whether the regulation of dual use should or should not apply to quantum computing, but it is how this transfers really to what are the norms that are implemented and at which stage. So, by all means, I'm not against regulations, and I know that for technology, for exponential technologies like quantum computing, dual use is something clearly that needs to be considered, but how this is transferred let's say, limitations like actions that limit international collaborations and actions that may inhibit really the development of the technology. This is what we should really be careful of, and this is what we should look at, and this is what we should discuss more openly, because I'm not satisfied with what is happening actually in quantum at the moment, precisely because of what I mentioned before.
Yeah, I mean, in a way, this kind of comes back to that question of, are we worried about the right stuff? This one's for the benefit of the audience. From your perspective, you're the elected business representative here. Do you think in the business community, not necessarily just at Bell Labs, these questions are being tackled and at a community level, behind the scenes, before we even get to hear about the good or the bad, it's being dealt with? Would you say that's fair?
Yeah, I will answer your question a little bit more from a Nokia or communication networking perspective. I think Nokia, we built network infrastructure, communication technologies, which are prevalent in everybody's lives today, consumers, but also enterprise, industrial applications, so forth. So certainly, it's a little bit different to see AI in that context being dual use, being good or bad. There's one exception to that. I think the one that we face more is because networks are so critical to support a lot of the applications that everybody wants to run. We use it mostly in consumer, but what happens if these networks are now used in defense and military applications? So we face it more from that perspective. But I think the part touching on AI, where it's good and bad, is sort of a cat and mouse game on AI on a cybersecurity perspective. We put a lot more AI into our networks to harden the networks, improve the performance, but then on the other side, you face actors and agents that use AI to attack the networks. And you get sort of, it's not so much for me on the AI in networking a good or bad use, it's more of a cat and mouse game between what you might define good AI versus what you might define as bad AI. Right? Of course, good and bad is relative to your viewpoint, but that's more where we face it. How do we accelerate our use of AI in networking, knowing that others will use AI to attack the networks, which are critical to everybody's daily lives?
I think we've conclusively proven this is a hard question to answer. With the number of minutes that we have left, I'm trying to turn all of these sessions into a sort of a take-home message, a mental framework. I wonder if we can come up with some guiding principles here that touch on what we've been talking about. A kind of, you guys know this question was coming. I warned you just off stage. We don't need to come up with 10 commandments, but can we come up with a few commandments on the development from the practitioner's point of view, how to get closer to a utopia or at least block off the paths to dystopia? Karl, you want to start?
I think one principle is there's a period of unfettered exploration that's absolutely critical. I'd like everybody in the room, to the extent that they can, in their conversations with friends, colleagues, policymakers, to try to foster a spirit of exploration without necessarily thinking about applications or economic considerations. I think that's to me where the big breakthroughs come, the most radical transformative changes that could positively affect the world will come. And then, of course, after that period of exploration, then there's a funneling down, an alignment with human values. But I think most importantly, the first commandment should be explore and follow what's beautiful.
Yes.
And then the second commandment?
Well, the second commandment, I have now, and suddenly I have two, because
one
is related.
Three, that's fine.
One is related to what you just said, and because you made me think of our one of our company values, that is crazy in thinking, rigorous in verifying. So sometimes we think a lot. We like to explore, but we are also having biases because we are so much into our own thing that we lose perspective. So being aware of biases and trying to be very rigorous when we assess our results and our technologies is really important. And then, of course, the first one for me really is even trivial: integrity. Integrity as a scientist, integrity as a CEO of a startup is the key thing. It's just, I think, should be our guiding principle.
Would you like to add to the commandments?
Sure, I'll add to.
They're being carved in stone backstage.
We'll see how far we get. So I would say one is always innovate with purpose. Know why you're innovating. I think the other aspect we haven't touched on so much is education. And I think we developed the technology, but we need to worry not about the change that technology brings, because you cannot really stop progress of technology, but we have to worry about the rate of change. And I think even now, compared to maybe 20 years ago, 50 years ago, 100 years ago, in previous industrial revolutions, the rate of change was slower. And I think even between the three technologies, if you think about AI, quantum, or optogenetics, the rate of change and the time frame over which they impact our lives are very different. So I think we need to worry about the rate of change and worry about how we educate everybody at large about the potential, good, bad, and maybe not so good, about the technology. How do we bring the technology, the new technologies, into the curriculum at middle school, high school, universities? How do we train and retrain and upskill current workforce? And I think we're not spending too much or not enough time on that. We're worrying about a bad end state, but we're not doing enough to prepare, keeping the positive in mind. So I would say innovate with purpose, be curious, be positive, but also take into account the rate of change. And we need to change. Education in 2025 should not be the same as in 1925 or 2125.
Sure.
But how do we bring these new technologies in and be optimistic about the technology?
Great. Everyone, thank you very much for this. It has been, I have a mental framework to take away from this. Thanks for your time.
Thank you.
Thank you.
If I could ask you to take your seats.